Hello, everyone. My name is Jian, and today I'm very happy to share with you some of our recent research, which is improving prediction-based lossy compression dramatically via ratio quality modeling. So to start with, we know that nowadays large-scale scientific simulations can generate extremely large amount of data. For example, like NICS and HAG as cost-merging simulations, they can generate petabytes of data per simulation. And these large amount of data can be heavy for storage system and I/O bandwidth for supercomputers and clusters out there. And typically we'll be using lossy compression to compress these scientific simulation datasets because of its high compression ratio without compromising the post-hoc analysis quality or visualization quality. And also the newly proposed lossy compression will actually provide different compression modes to control the compression error for scientists and users. So you can see here actually is a visualization on the NICS simulation compared with the original one on the left-hand side. The compressed data sets will actually shows basically the same visualization characters compared to the original. And in order to take advantage of these lossy compressors, we actually need to identify the optimal trade-off between the compression ratio and the compressed data quality. However, prior to this research, there is no analytical model available, and the trial and error experiment is used to identify this optimal trade-off. What is trial and error is basically to compress and decompress data with different feasible error bounds or a combination of error bounds and measure the compression ratio and data quality to choose the best error bound. So you can hear that it's a very high computational cost, and also the identified configuration setting is dependent on the specific configuration and input data. So once we change the input data, or if we change the initial state of the simulation, we want to retune this configuration based again for the trial and error experiment. So it's another time-consuming thing. And in this research, we want to propose our ratio quality modeling, which is to provide an estimation on the compression ratio and the compressed data quality with mainly three goals. One is to have a general model suitable for most scientific data sets and simulations out there. And also we want to provide a very high accuracy on the estimation, and also a very low computational overhead, especially compared to the trial and error approach. And the contribution of this research mainly is that first we decoupled the prediction-based lossy compression to build a modularized model so that we can analyze each module and then assemble them together at last to predict the ratio and quality. And second, we theoretically analyze how to estimate the encoder efficiency and provide essential parameters for compression ratio estimation. Third is that we propose a theoretical analysis to estimate the qualification of lossy decompressed data on post-hoc analysis. And lastly, we evaluate our model on 10 real-world data sets with 17 data fields. And also we demonstrate the efficiency and the performance of our model on multiple use cases. So some of the backgrounds here is that first, we know that there are multiple data management libraries in scientific applications such as HDF5, NetCDF, or ADIOS. So in this research, we actually use HDF5 as an example in the evaluation section, but note that our approach can be adapted to any other data management libraries here. And most of these libraries will actually has compression techniques adopted. So on the right-hand side, you can see, for example, the parallel application will generate the data, and these data management library will basically provide a data filter, for example, here, which is compression and decompression. And then then the compressed data will be passed to the data management library, and then the parallel and etc. And for the error-bounded lossy compression, there are actually basically two types of them. So one of them is transformed-based lossy compression, for example, like ZFP. Another is prediction-based lossy compressor, which is SE in this case. So in this research, we are focusing on the prediction-based lossy compression. And we actually have multiple like data distortion metrics, for example, like PSNR, SSIM, peak signal to noise ratio, structure similarity, to evaluate the data distortion after decompression. So for each of the error-bounded lossy compression, there will has different compression modes to control the error control the compression error, for example, the error bounded mode or fixed rate mode. Error bounded mode, for example, like absolute error bounds, the user will define an absolute error bound so that the compressor will compress the data and the decompressed data compared with the original one will be within this absolute error bound for each single data points. And the fixed rate mode is actually only applied in the transformed based lossy compression. And in general, the fixed rate mode will provide a worse compression performance compared to the error bounded mode. That is, it will typically have worse data distortion in the under the similar compression ratio or lower compression ratio under the similar data distortion. So in this paper, we're actually focusing on the prediction-based lossy compression. And here is a very brief introduction on it. So what it does is each data points value is predicted based on its neighboring data by different types of predictors like Lorenzo predictor or linear interpolation predictor. And then after prediction, the predicted value compared with the real value, and this difference will be quantized into quantization code. And then note that this quantization code is already lossy compared to the original one. And then the quantization code can be encoded by further by lossless encoders. And the main challenges when we propose our ratio quality model is that first, how to decompose prediction-based lossy compression into multiple stages, and how do we model the compression ratio for each stage, right? And then how to reduce the time cost for extracting data information, because we need some of data information to predict the compression ratio or data quality. And the third is how to model the quality degradation in terms of diverse post-hoc analysis metrics. And the last is that how does our model benefits real-world applications? And in order to answer those challenges, here is an overview of our proposed rate quality model. So we can start from the upper left here, the predictor. It will actually provide the prediction error to the quantizator section, and the quantizator will provide the estimated error distribution. And this is for the post-analysis to estimate its error distribution. And then also it will provide the quantization code histogram to the encoder section. And in the encoder section, we will estimate the encoder efficiency on Huffman and all the other optional losses compression after Huffman. And this will basically provide the compression ratio estimation. And once we have this ratio quality model, we can actually use it to optimize for multiple optimization purposes, for example, like memory compression, overall ratio quality. We'll talk them in detail in the evaluation section. And this will actually provide the predictor and the error bound configuration for compressing the data. And the analysis, the theoretical analysis for this mainly has 3 steps. One is that we want to model the compression ratio of popular encoders, Huffman and other losses, and refine the compression ratio model for various predictors and quantizers. And also we want to model the quality degradation for the post-analysis for the generic and the specific post-hoc analysis. So first, let's look at the modeling encoder efficiency. Note that the encoder will actually encode the quantization code, and the quantization code is actually highly randomized after the predictor based on our experiment. And the encoding efficiency provided by Huffman encoding is highly separated from that provided by optional lossless encoder. So you can see on the left-hand side, this shows the compression ratio provided by Huffman and all the other lossless encoder after Huffman. And it is only after error bound is larger than a certain point where the Huffman encoder reaches its limits, in this case is 32, can other lossless encoder provide additional compression ratios here. And also we note that the red dash, after the red dashed line, 0 would actually dominate the Huffman codes because the prediction error is highly centralized. So when Huffman encoder reaches its limits, most of the Huffman code would be 0. And that's why we can use relance encoding to represent all the other lossless encoder after Huffman to basically to estimate the efficiency to encode the spatial information. And we will demonstrate in the evaluation section that even though we use relance encoding to represent all the other lossless encoder, the accuracy is still very high. And you can see when we separate the Huffman encoding and relance encoding efficiency, and all the efficiency estimation is based on the quantization code histogram P here. And also we have a reverse equation to estimate the error bounds based on the targeting bitrate or targeting compression ratio. And next, for the modeling quantize the prediction error histogram, it will mainly has two parts. One is a prediction error histogram, and the second is a quantization code histogram. So for prediction error histogram, we actually proposed a different sampling strategy for different predictors: Lorenzo, linear interpolation, linear regression. And also on the right-hand side, this figure demonstrates how we chose the sampling rate for all the predictors. And eventually we choose 0.5 for all of them because it provides a very low sampling rate and also a very acceptable error prediction error. And then for the quantization code histogram is it can be computed based on the sampled prediction error. However, on large error bounds, it will actually have a large distortion because in the sampling, we use original value to predict all the other values. However, in the real prediction-based lossy compression, it will actually use predicted value to predict the next value for the consistency on the decompression phase. So that will cause a difference. So you can see here, for example, if the original value is 0 and 1.3, the quantization code using original value would be probably 0 and 1. However, if we use a predicted value, it will probably be 0 and 0. So that is a different quantization codes. And we actually solve this issue by proposing a bin transfer scheme on the larger error bounds when the error bounds is becoming very large. And the detailed analysis is in the paper. And next, for the post-hoc analysis quality model, we actually propose, first we propose the error distribution described by its variance. And in most cases, the error distribution, the compressed error distribution will actually be a unified distribution. However, on a very high error bounds, we need to refine this distribution to centralize the distribution. And you can see on the right-hand side, this figure demonstrates the necessity of refine the centralized distribution compared with just using the unified distribution in post-hoc analysis. And we also introduced an example of two post-hoc analysis model on PSNR and SSIM. You can see we provide the estimation on the both of them based on the error distribution, and we also provide a guideline on how to use data, how to utilize the error distribution to estimate the data-specific post-hoc analysis. And here for the evaluation section, we demonstrate first is our model accuracy. So all the figure here you see the solid line is our prediction and the dot are the actual experimental results. So on the left-hand side, this is a compression ratio accuracy. So there is two colors, blue and red. The blue line means Huffman encoding only, and the red line means Huffman encoding plus lossless encoding after it. So you can see on both situations, our estimation is very accurate compared with experimental results. And on the upper right-hand side is the PSNR estimation accuracy, and on the bottom right-hand side is SSIM estimation accuracy. And similarly, we can see that our estimation is very close to the experimental results. And note that we can also see the refined error distribution takes advantage in the PSNR estimation accuracy under very high error bound situation. Similarly to that, we also evaluate our model on 10 data sets and 17 data fields. And in this chart, we can see basically all the data sets and data fields, our model can provide a very low prediction error. And also note that lossless prediction error is basically slightly higher than the Huffman prediction error. This is because we use redundancy encoding to represent the lossless, all the lossless encoders. So that will introduce slightly more error to it. And also for the post analysis here, PSNR and SSIM, our proposed model can also estimate PSNR and SSIM pretty accurately with only with a very low prediction error. And for some use cases here, first of all, we propose that our model can be beneficial to the predictor selection situation. So here you can see on the right-hand side is the rate distortion on three predictors: Lorenzo interpolation and regression. So especially on the blue and the red line here, we can see which represent Lorenzo and interpolation. So we would like probably to use interpolation when bitrate is fairly low or and high, and Lorenzo when bitrate is fairly high for the best PSNR possible. So also we can see the solid line is our prediction, and based on our prediction, we can actually already provide the prediction selection based on the different bit rate before we actually compress and decompress the data. And the second use cases we propose is the memory limitation control, which is under some memory limitation situations, we want to efficiently utilize these available memory to compress the data as far as possible with a given memory. And on the right-hand side is that the dashed red line is our target compression ratio or the target memory utilization. And we can see among our evaluation group of 15 groups, we can always provide a very high efficiency, very high memory efficiency when utilizing the memory space here. And we have a specific scheme to compress the data so that it can be within the memory limitation. And the detail will be included in the paper. And the third use case here is the in-situ compression optimization, which is slightly complicated than the other two, is that for most scientific applications out there, we actually have different data partitions or different timestamps. And for different data partitions, we actually want to compress them with different compression configurations. For example, those data partitions with higher information density, we want to compress it with lower error bounds, right? So on the right-hand side, this demonstrate we compress compared with the traditional approach, which is the red line here, which is to compress every single timestamp with the same compression configuration. We can actually use our model to in-situ tune the compression configuration for each timestamp based on its own property, and the compression separately with different compression configuration, the shown in the blue line here, and further improve the overall compression ratio of the entire simulation without compromising the post-hoc analysis quality or the visualization quality. And in terms of the performance, our model actually provide a significant lower overhead compared to the previous solution. So on the right-hand side, you can see our solution compared with the previous solution, which is to sample blocks of data and compress, decompress, compress, and decompress to figure out the estimated compression error for the entire data sets. And compared with the previous solution, our solution also only needs one sapling to predict the compression ratio on all the other error bound settings. So you can see only the first red block is slightly higher than all the other red blocks afterwards. And also, our approach outperforms the trial and error solution by 18.7 times on average when considering 7 candidate error bounds and two predictor candidates, Lorenzo and interpolation. And more specifically, we also evaluate the overall performance of data management. So you can see the upper figure here, we actually compared our solution to the traditional solution, which is also to apply the same compression configuration among all the data snapshots. And you can see for some snapshots, for example, the 1600s or 1800s, the bit rate is very high, which is the compression ratio is very low when using the traditional approaches. However, with our approach, we can optimize the compression configuration for each snapshot so that each snapshot will have a similarly low bit rate, and also all of the snapshots will satisfy the required PSNR for post-hoc analysis. And also with this benefits, we can actually provide consistent and the fastest data dumping time. So on the bottom figure here, you can see we compared the data dumping time of using our solution and previous traditional solution. And also we introduce our implemented in-situ trial and error approach, which is to do the trial and error for each snapshot in-situ. However, this will also introduce a very high overhead for the optimization. And compared with our solution can still provide the fastest data dumping time and provide a consistent data dumping time that is beneficial for the scientific data management libraries. And that's all. Thank you.